Sorry. So let me try again. In computer science, we often have an expensive function that we want to evaluate on many inputs. And in fact, these inputs are often related, so we can compute the outputs more efficiently than by evaluating the expensive function from scratch. And that's what the field of incremental computation is about. For example, the input may be a database, and the expensive function could be a database query. After making a small change to the database, such as inserting, deleting, or modifying a single row, we don't want to redo the whole computation, but we only want to do the necessary work to update the output. And what's more relevant to the session is that the same pattern shows up when inferring the distribution of a probabilistic program. The inputs are program traces, and the expensive function is the density evaluation according to the probabilistic program. Inference algorithms like Markov chain Monte Carlo make small changes to the trace, such as changing a parameter, inserting a cluster, making a Gibbs move, etc. By the way, if you don't know these concepts, I'll explain them in a minute. But here as well, we want to compute the new density functions, density values incrementally. In fact, this is critical for scalable inference. Typically, if you naively evaluate your densities, your inference algorithm will scale quadratically in the size of the data. But by only recomputing what's necessary, you can get it down to linear running time. You could achieve this by writing your inference algorithm by hand, but that is difficult and error-prone. So what we'd like to do is, for our probabilistic programming systems, to automate this. And indeed, many existing probabilistic programming systems do actually provide some form of incremental computation. These incrementalization schemes can be fairly complex. For instance, some of them construct elaborate dependency graphs, and since we're dealing with probabilities, even the existence of nodes in the dependency graph can be random. Such complexity makes this prone to bugs that may even result in wrong inference results. And in many cases, existing systems are still asymptotically slower than a manual implementation. To address this, our main idea is to reduce the problem to deterministic incrementalization. So we first transform our probabilistic program to a deterministic program for the density function, and then incrementalize this deterministic program. This means we can build on all the research done on incremental computation outside of probabilistic programming, and in addition, this modularity simplifies reasoning about our approach. We make contributions to both this density transformation and the deterministic incrementalization transformation. But before I get into the details of our approach, let me give you a concrete example. Suppose you're given a set of data points, and you want to find clusters in them. One possible approach is to reason about how the data may have been generated. And for that, we're going to use a probabilistic program. A probabilistic program is an ordinary program extended with the ability to draw random values from a distribution. So given a number n of data points to generate, this program first samples the number of clusters from a geometric distribution, written with a tilde. And behind the scenes, the probabilistic programming system collects all the random choices in a data structure called the trace. For example, when this line of code is executed, the system might sample 4 as the number of clusters. I'll also visualize this trace on the top right as we step through the program. The clusters are represented by these blobs. Next, the program samples parameters for each cluster. The mean determines the location, and the covariance the size and shape. Then it samples a weight for each cluster. A higher weight means that more data points belong to this cluster. Using these weights, each data point is assigned to one of the cluster indices. For instance, the first data point is assigned to cluster 1 in blue. Finally, we loop over all the data points and sample a random location based on the parameters of the assigned cluster. Different executions of this program can lead to very different traces with a varying number of clusters. Obviously, our goal is not just to generate random datasets or random traces, but to infer the clusters given a set of points. So if we're given these data points, we want to find program executions that could plausibly have generated them. In other words, we want to find plausible execution traces where the data part is exactly the given data points. A very popular and effective approach for this is our Markov chain Monte Carlo algorithms. And what they do is they essentially search for good traces. And I'm going to show you how this works in a slightly simplified and sped up way. We start with an arbitrary initial trace with the fixed data points. And typically, this will be a bad explanation of the data, like here. Next, the algorithm makes changes to the trace, such as reassigning data points to different clusters, or changing the cluster parameters, or splitting a cluster, and so on. And in this way, it constructs a chain of traces whose distribution converges to the posterior distribution of the probabilistic program, conditioned on the given data points. Now let's look closer at how the traces in the chain are sampled. So starting from the initial trace, we consider a set of proposals for the next trace. Here, the proposals are different cluster assignments. The programmer can specify these proposals or fall back on default proposals by the probabilistic programming system. Next, we score each proposal using the density function of the probabilistic program. High density means that the trace is plausible or likely to have been generated by the program. And based on these densities, one proposal is accepted as the next element of the chain. And then we keep going the same way. We start with this trace, and this time the proposals change the cluster parameters. The proposals are again evaluated by the density function, and one of them is accepted, and so on. For all of these proposed traces, we essentially have to rerun the probabilistic program to evaluate the densities. And we have to do this at every step of the inference. So this dominates the running time of the inference algorithm. But note that all the proposed traces are very similar. They only differ in their cluster assignments on the previous slide, or in the cluster parameters, as we see here. So we can save a lot of time if we can find a way to compute the density incrementally. So coming back to our main idea, we have two program transformations. The first one turns a probabilistic program, which generates traces, into a density function, which evaluates traces. The second one turns any deterministic program, for instance, a density function, into an incremental one, which can efficiently process input changes. And when we combine these two transformations, we can incrementally evaluate densities and speed up inference. Let me first discuss the incrementalization. So what are the key ideas? We're going to build our approach on ideas from the incremental lambda calculus. This calculus is a formal framework for incremental computation in functional languages. And a key idea is to make changes to values explicit in the language. Every type tau has an associated change type delta tau, which represents changes to values of type tau. And these change types are defined recursively on the type grammar. There are many ways of choosing concrete change types, but for our setting, we found that the following choices worked well. I'll explain them in a second, but first, some motivation. Why did we pick these? Well, the change type is supposed to track what has changed about a value, so that we can avoid unnecessary recomputation. For example, when we loop over a collection, like a list or a map, it is crucial to know which elements of the collection have changed, so that we can skip loop iterations for unchanged elements. This can lead to asymptotic speedups, which is why our change types for collections are very fine-grained. For instance, the change type for a map data structure records removals, modifications, insertions, and insertions of elements. The change type for records is a subrecord, which is like a record of changes, except unchanged fields may be omitted. By contrast, knowing exactly how a real number has changed typically doesn't help you avoid a lot of work, so we use a simpler, coarse-grained change type for base types, like booleans. For these, we just record the new value and whether it changed at all. Furthermore, in the incremental lambda calculus, every primitive function, such as arithmetic operations or list operations, all of them have incremental versions operating on change types. And these incremental primitives serve two main purposes. First, they precisely propagate change information. They describe how the output value changed given changes to the input. Second, they aim to exploit the change information to avoid redundant work when recomputing the output change. The overall program transformation then stitches these incremental primitives together and ensures that all the changes are propagated downstream to exploit opportunities for incrementalization. What do these incremental versions of a function look like? Well, a couple of versions have been proposed in the literature, but they all have some serious drawbacks. So in the original incremental lambda calculus, a function f has a derivative delta f from an original input and an input change to an output change. This serves the purpose of propagating changes forward. But a big downside is that only some derivatives are efficient to compute. When the input change alone determines the output change, then f is called self-maintainable and the derivative is efficient, but most functions are not self-maintainable. And that's the motivation for a version of the incremental lambda calculus with caching. So the caching version of a function returns the output and in addition a cache of intermediate results. The derivative now also takes in a cache and outputs an updated cache. This allows it to be more efficient and also works for functions that are not self-maintainable. It creates another problem though. The composition of two functions needs the caches of both individual functions. So we quickly end up with huge caches everywhere whose types depend on the implementation of f and not just its type. All of that is cumbersome and complicates correctness proofs. We address these problems with an abstraction called updaters. So we model updaters as a co-inductive type that sends input changes to output changes, plus a new updater for subsequent changes. Concretely, an incremental function takes an input and produces an output, but in addition, we get an updater. That updater, in turn, accepts changes to the input and produces changes to the output, as well as another updater. And this updater takes input changes on top of the previous change and produces output changes on top of the previous output change, and so on. How do the updaters work on the inside? To construct them, you provide an initial cache value and an update function from an input change and a cache to an output change and an updated cache. And when you apply an updater to an input change, it forwards that change together with the cache to the update function and constructs a new updater from the new cache and the same update function. As a concrete example, let's consider the incremental version of the length function for a list. So this function returns the length of the list, and it constructs an updater whose cache is the length using the makeUpdater construct. The update function accepts an input change and the cached list length, and the new length is just the cached length plus the number of inserted elements minus the number of removed elements. And finally, it returns the change value for the length, which contains the new value and a flag indicating whether it changed, and also the new length as the new cache value. So in summary, the updaters encapsulate their cache types, and we can still stack changes on top of each other, which is important for probabilistic inference. So now let me put all the pieces together and summarize how the incrementalization transformation works. We start with a deterministic function from an input type to an output type, and such a deterministic program is incrementalized to a function that takes the same input type, but in addition to the output also produces an updater. A lot of this was inspired by the literature on the incremental lambda calculus, but our approach also works in the typed higher order setting. Each primitive operation in our language has an incremental version, and our program transformation composes them together. And since we have a higher order language, we can treat loops as a special higher order primitive, where the loop body is an argument. The incremental versions skip loop iterations by caching intermediate results, and our other primitives are designed to propagate precise change information about collections, so that when we get to a loop that iterates over such a collection, we can save a lot of work. And this is what leads to our asymptotic efficiency gains. Now let me quickly talk about the density transformation. It transforms a probabilistic program into a deterministic program, taking a trace as input and producing a result value and the density for this trace. The basic idea is that sampling from a distribution is transformed to evaluating the density function of the distribution at the corresponding element of the trace. For example, if we have a program sampling x and y from two distributions, the density program will take the values for x and y from the trace and compute the density of the value for that distribution. All of these subdensities are multiplied together and returned as the total density together with the result. Such a transformation is standard in the probabilistic programming literature, but in our setting, things are a bit more interesting because we support unordered collections and unique name generation. If you want to learn more about how we do this, come talk to me afterwards, or you can also read the paper. But I want to quickly explain the motivation for the existence of these features. Having types for our traces with a rich structure is important because when we incrementalize the density function, it will work on a richly structured change type for traces. This way, we can have concise descriptions for lots of changes, like removing a cluster. In fact, the notion of trace types has been described before, but our trace types are more expressive. So how do we assign a type to the traces of a program? The idea is to mirror the control flow that generated the trace. For example, a sequence of sample statements has a record type, recording the type of each subtrace. Iterating over a list produces a list of subtraces, and in our work, we added unordered iteration, say over a set of names, which produces an unordered map from names to subtraces. Why does our language have fresh name generation? This is also motivated by our desire to keep changes concise. To see why, consider the clustering example again, where we index clusters as 1, 2, 3, and so on. Now suppose we delete cluster 1, which yields a new trace below. Then all the assignments have to change, because all the other indices are shifted down by 1. And this destroys incrementality. Instead, if we give each cluster a fresh name or ID, things work out much better. The assignments are now a list that assigns each data point to the name of a cluster rather than an index. And now if we remove a cluster, this only affects the data points which were assigned to that cluster, and the rest is unchanged. Okay. All of this was to explain the compositional approach to incrementalization. But a key property of our approach is that we can prove correctness properties. So we proved both stages of our transformation correct. And thanks to working in the type setting and our updater abstraction, we were able to use denotational semantics and logical relations arguments in the proofs. We also implemented our techniques in Julia and evaluated it for a number of inference programs and models. Specifically, we compared our implementation with full recomputation and the experimental fine-grained incrementalization in the GEN system. And we evaluated several MCMC inference programs on a variety of models. And in the plots, you can see that our method in blue is faster than the other methods, and the running time grows more slowly in the size of the data. The takeaway is that our method is the only one achieving the same asymptotic running time as a manual implementation for all these benchmarks. And you can find more details in the paper. Speaking of the paper, there's a lot of cool stuff that I didn't have time to talk about, both for incremental computation people and for probabilistic programmers. And yeah, this concludes my talk. Thank you very much.
All right, any questions? Maybe I have one quick one.
Yeah.
So you mentioned probabilistic programs or programs with sampling instructions. Do you also consider conditioning?
The conditioning is not an explicit operation in the program. It's rather that once the program is written, we constrain the traces to the program. For example, I had this. This is going to take a bit. But basically, the idea is that we fix the data part of the trace here. Mm-hmm. And yeah, only. But this is not in the program directly. This is constrained afterwards. Yes.
But it's implicitly.
Yes.
All right. Thank you. If there are no more questions, let's thank Fabian again.